Have a look at the idea of finding limits. And as I say, this will come in handy for the next thing that we want to do. A couple of techniques. First technique, and hopefully we can use this, and that's just direct substitution. So what are we saying with this? What we're saying is we've got this graph, y equals x plus 7. We're interested to know what is happening to this graph as the x value is getting closer and closer to the value of 5. Now this one here I can do by directly substituting in and go, well, 5 plus 7 is 12, so it must be approaching 12. So you get something like that, you beaut. Doesn't always work though. So this next one is where we factorise and then cancel. See, look at this one. X squared minus 9 over x minus 3. If we substitute 3 straight into that, I'm going to get 0 on the top of the fraction, but I'm going to get 0 on the bottom of the fraction as well. And so we have that age-old problem, 0 on 0, what is it? Some people will say, oh, it's 1, because anything on top of itself is 1. Some people will say, oh, it's 0, because 0 divided by anything is 0. And then others will say, well, hang on, it can't be, because you can't divide by 0. So how do you have 0 on the bottom of the fraction? So we have an issue with this problem. We can't all come up with different answers for it. If we can, factorise and then cancel. So the top of the fraction, difference of 2 squares, the x minus 3 cancels. We then get something that we can directly substitute into. So 3 plus 3 is 6. So the value of that will approach 6. If I had to draw that graph, we would have a point discontinuity at x equals 3. It can't actually equal 3, or x can't actually equal 3, because you can't substitute it in. But now, the limit that I'm really interested in looking at is this special one. And in order to use it, I want to point this out. See, because infinity, how do you substitute infinity into something? I mean, you can't really, but we're talking about limits. So we're not actually substituting in infinity. What we're saying is, as we get closer and closer and closer to infinity, if that was possible, what would the y value be doing? To help, here's a curve we know what it looks like. 1 over x is our basic hyperbola. So our basic hyperbola, as x is getting bigger and bigger and bigger and bigger, and we're getting closer and closer to infinity, that y value is getting closer and closer to 0. So using that limit, it'll help us with questions like this. Whoa. So we want to substitute into x cubed plus 3x squared plus 2x minus 1 over 4x cubed minus 1. Now at this stage I can't do it, because if I did, I'd go top of the fraction. Infinity's like the biggest possible thing we could have. But now I'm going to cube it. So that's like really, really big. But then I'm going to add 3 times infinity squared. Wow, it's just become huge. Plus 2 times infinity. Oh, it's just even bigger again. Minus 1. So what? You know, we've got this gigantic thing. All right, so really big thing on top. Now we go to the bottom of the fraction. 4 times infinity cubed. Oh, that's really big too. Subtract 1. Yeah, okay. But now I've got this really huge thing divided by this really huge thing, and I've got no idea what it is. The only thing we know is that when we, for want of a better word, substitute infinity into the bottom of the fraction, we will get 0, or it will approach 0. It's probably a better way of saying it. So every single one of these terms, I want to change it to I'm substituting into the bottom of the fraction. So we will divide everything by x cubed. Now why did I choose x cubed? Because that was the highest power. So that means every one of those terms now, when we cancel, will either be a constant or something with x on the bottom of the fraction. We know that all those terms that has x on the bottom of the fraction, when I substitute in infinity, or can't substitute in infinity, as we pretend to substituting in infinity, we'll get 0. Therefore I'm left with 1/4. So that'll approach 1/4. That actually means I can do this a lot quicker, because that pattern is reproduced every single time. Because essentially, look at the answer. The answer is 1/4. Look at the original question. How does 1/4 come into play into that? Well, that was the coefficients of that highest power that we divided by. So all I really got to do is have a look for the highest power. Whatever the coefficient is, that's what I'll be left with. So for our second example, the highest power there is 3. So I'll be left with 0 on the top, because there is no x cubed term on the top, and on the bottom the coefficient of x cubed is 1. 0 divided by 1, 0. How about something like this? Biggest power there is 7. So if I just look at the coefficient of x to the power of 7, 1/3. 1/3. Right. X cubed plus 2 on x squared minus 1. X cubed is the highest power. So I get 1 on 0, which is undefined, so it's probably going off to infinity. We tend to think of 1 divided by 0 as, well, we know it's going to be really big, because the smaller the number you divide by, the bigger the actual number. So that'll be going off to infinity. That gives us another way of finding horizontal asymptotes. Because remember, we said a horizontal asymptote is what is happening out at infinity. So it's the same question. What's the limit of this function as we approach infinity? The powers, x squared is the highest, so I'm left with 1 on 1, which is 1. So the horizontal asymptote is y equals 1. So that's an alternative way of finding the asymptotes. Look, our textbook doesn't actually have an exercise on this. So I've taken one out of the Terry Lee book. Not sure whether it's his new version or his old version, but exercise 6.1, it is in the sheets. Because I don't see how we're going to do the next bit of theory tomorrow without having done something on limits.